Okay. Good morning. Good morning. Technically, it's morning. It's like 1 in the morning today. For your guys's lesson for the day, I'm thinking of just recording for an hour or an hour 15, whichever, right? So you guys can watch this lesson in your own time, right? This will be topic six, right? Topic six. We will start with topic six immediately, right? And well, this is in line because next time we will have thermodynamic cycles part 2, right? This Thursday. And then on week 13, right? On week 13 we will have part 3. And then on the Thursday of that we will have a preparation for your final exam. So you can ask me literally anything in that time, okay? So, all right, let's begin. And of course, for an overview, we will have a lot of things scheduled, right? This is why it's also three parts. We will have the first law of thermodynamics for cycles. We will have the different kinds of cycles, power and reversed cycles. And we will tackle the second law of thermodynamics as to why that's so important. Okay? And yeah, again, this will be an info dump session. So please digest at your own pace, right? If it seems that I'm going too quickly, then either slow me down or watch me at another time, right? If I'm going too slowly, then, well, the speed button is for you, right? And again, just like before, right, we have to anchor our thermodynamics learning based on a particular purpose. And I suppose for topic six, I feel it would be best that we end our discussion on thermodynamics with, I don't know if I should call this a cautionary tale, pero studying thermo is not only a way for us to understand the world, it's not only a way for us to manipulate the world as it is for our benefit, but also now, I feel like it is also very important for us to study thermo as a way to understand just how limited things are actually in the physical world, right? We can't just do everything, right? We can't just make up some thing, right? Mass just doesn't come out of thin air, right? There's always an explanation for everything. And ngayon, we will find out exactly what we can do, right? What we can do. And so, oh, sorry. And so, let's begin, right? And it's always, again, with a quote, if you throw a tumbler full of water into the sea, you cannot get the same tumbler full of water out again. So, medyo nonsensical yung quote natin, but you will understand why later. Again, this is by the great ECE Lord James Clerk Maxwell. Again, I don't know why he's in thermodynamics a lot, but okay. I think it's in statistical thermodynamics that he shows off. But anyway, let's begin immediately with cycles and the first law. So I've been teasing somehow, somewhat, cycles, right? If you guys remember in problem set 3, there's a big table there, right, with 8 processes, and I said that that was a cycle, right? For the people who have tried, right, who have tried to understand what the pattern was, then congratulations, you are now a bit more informed, right? But ayun nga, for the rest of us, right, what are cycles? I will start off by defining cycles based on our definition of states and processes, right? If you guys remember, a state is best, excuse me, is best described as a snapshot of a system, right? How do we know it's a snapshot of a system? Well, we know it's a snapshot of the system based on the properties that we measure, right? Either the temperature of this system at this particular state is ganito ganyan, or the volume is blah, 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 right? And we have to also be aware that this state is not time-based, right? A state could be a really long time as long as they all have the same measurable properties, right? And therefore, if you want to go from one state to another, you go through a process, which is an event where a system transitions from an initial state to a final state. Again, both of these processes have to do with quasi-equilibrium. If you guys remember what that is, that means that every state we're talking about is actually what we call an equilibrium state. Right? An equilibrium state is basically where nothing changes, right? Where nothing is prone to change. In a process, is in quasi-equilibrium if every state that you go through is an equilibrium state, right? Just another kind of definition from our topic 1. And finally, we have a cycle. Very self-explanatory, pero a cycle is basically a series of events where the initial and the final states are the same, right? That's it. Cycle nga, diba? Right? Exactly. So now, this thermodynamic cycle is where we will base our discussion for this topic, right? We will spend like what, 4 hours on this thing? So something like that, right? And basically now, let's try to understand these definitions more clearly based on a graphical kind of approach. I will have here a PV diagram. Your P is in the y-axis, your V is in the x-axis. And so we will have just these guys for now here, right? If I want to say, or if I want to specify a particular state, how will I put it in the graph? Well, a state is just going to be a point, right? This point is going to be state 1. How can I know it's a particular point? Because it is a state and that state has measurable properties. In this case, because we are trying to graph, right? Because we are trying to graph this thing on a Cartesian plane, we know that it has two coordinates, P1 and V1. Basically, the pressure at state 1 and the volume at state 1, respectively, right? And now, let's try to graph another state, a state 2. Right? Again, this state 2 has measurable properties at P2 and V2, the pressure and volume at state 2. And if you want to go from state 1 to state 2, you're going to have to undergo, or rather, the liquid or the fluid or the gas, right, has to undergo what we call a process. And the process, of course, is going to be, right, if you have guessed it, it's going to be a line between, it's going to be a line or a curve between the two states. And mind you, this is not the only process that is available out there, but I will call this process 1 to 2. What do I mean? This is a process. This is a particular process as well. This one, a straight line, is also a process, right? And this loopy one, right, is also a process. The thing about the process nga is that it is based on just the line itself, right? Whatever properties you may have about this process is specified to that particular shape only, right? And so let's proceed with another state, state 3. And if you want to again, connect states 2 and 3, what you're going to have to do is create a process, right? Yeah, process 2 to 3. And the thing about processes is that they have a direction, right? You have to go from an initial state, in this case, state 1, and end in a final state, which is state 2. At a process 2 to 3, in process 2 to 3, your initial state is state 2, your final state is state 3. And basically, if you want to create a cycle, you're going to have to create, well, basically, a series of events where the initial and the final states are the same, which in this case will be process 3 to 1, right? Kailangan all of the arrows need to point to each state, and then basically all of them have to end up to the initial state that we mentioned, right? Process 3 to 1. So 1 to 2, then 2 to 3, and then 3 goes back to 1, right? And so here we have a cycle, right? A cycle which has 3 parts, or rather 3 states, right? 3 equilibrium states. And so, based on this graphical viewpoint, we can say that states are points, processes are lines or curves, and, well, cycles are closed shapes. Ganun lang, right? And in this case, well, there is going to be a, there is going to be a natural next question, right? If you guys think about this, right, we have just successfully graphed 3 states, 3 processes, and one, what do you call this? One thermodynamic cycle. And, well, we are graphing it in a PV diagram. And so as a result, right, a completely natural next question happens. The next question would be, what is the area, right? What does that represent, right? And so I will now take you to this, right? Again, we have the original cycle that we drew earlier, right? And I hope you guys are answering along Hopefully you're answering along as I am discussing this. But what is this region that I've shaded right here? Right? What is this region that I've shaded right here? Hopefully, let me see how long I've been talking. 10 minutes, right? This is basically the work, the non-flow work, just to be completely sure, the non-flow work from state 1 to state 2. AKA, this is the work that you gain or lose, right? Gain or lose from transforming state 1 into state 2 via the process 1 to 2. Again, we are talking about a process here, and we are talking about work. Work is not going to be just based on the endpoints, right? Work is going to be different for all of these processes right here because, well, they're going to bound different areas, right? Different areas. And now, what about this? What about this region? Right? You will now see, okay, there's a pattern, right? This is now the work from process 2 to 3, right? And then now this thing. Why is it colored red? You might be asking. Because, well, I will tell you right now, it is negative. Wait a second. What do you mean negative? Right? If you guys notice, right? From state 1 to state 2, look at the volume, right? This is volume 1 and this is volume 2. What happens is that volume 1 is the initial state and volume 2 is the final state. Therefore, the volume increased. What is another word for volume increase? That means expansion. And when there is expansion, you should think about, okay, what is the sign of the work that I'm going to get? Right? The sign of the work you're going to get if your substance expands, right? Because because it expands, it's pushing out the piston or whatever you want to put on top of the gas. That means you work out. Right? Your work goes out, but rather the system does the work on something else. And same goes for state 2 to state 3 through this process 2 to 3. Right? It's another kind of expansion, therefore it is also positive. But now look at what happens when you're going from 3 to 1. When you're going now from 3 to 1, things change. Things change how? Because now look, right? It is now going to be a compression, right? Your state 3 goes to state 1, right? Your state 3 is now being compressed up until it gets to state 1. And as a result, well, now this is going to be negative. I'm not putting in the negative sign yet because I just know that the result of this will be a negative. Oops, sorry. This should be state 3 and this should be state 1, right? From state 1 to state 2, from state 2 to state 3. This should be from state 3 to state 1. Okay, but suffice to say, right? This is going to be negative because we can see from the graph that it is a compression process. Okay, hopefully that is natural naman for us. And now, this is something that I found so cool when I was making this PowerPoint presentation. But look, now, what happens? If you just see the area enclosed by this shape, that will just mean that it is the sum of these three works, right? Earlier, we were saying that, okay, I will add this area to my total, right? I will add this area to my total. And then for the second process, I will add this area to my total. And then what happened was that, well, now I will remove this area from my total. What will be left? Right? The thing that will be left will be this triangle or triangle looking thing. And that will be this area enclosed by this shape, which is just going to be the sum of all the works, the non-flow works of this graph, of this cycle, right? Sum of the work, the non-flow work from state 1 to 2, the process 1 to 2, sum of the work from process 2 to 3, and 3 to 1, right? If you know, right, if you know the areas of them, you can get immediately what we call work net, right? Work net. For the people here who are interested what this is what we call, whoops, I have yellow pala. Sorry. For the people who are interested in this is what we call a contour integral. Basically, if this is a more predictable shape, like for example, I don't know, a circle, an ellipse, ganon, a contour integral allows us to be able to immediately compute for the area inside of the shape. Right? But this is just a bunch of functions. We don't have a clue. Might as well just have all of these works summed up. And this is what we call network or work net. So if ever you see a question with network or minsan, they get bunched up into one word network. This is actually what we mean. Work net. Okay? And so now basically, again, states are points, processes are lines or curves, and cycles are closed shapes. That also means that the area enclosed inside a shape is what we call the network. Okay? Now, we bring back, right? We bring back the most important law of all thermodynamics. Basically, energy cannot be created nor destroyed. Why are we bringing this back? Because now, at the very least, alam nyo na. You guys are now aware of the graphical viewpoint in here. And now what we need now, I said the word now a lot there, right? And what we need is now the mathematical model, right? Q minus W is equal to your change in energy. More specifically, for steady flow processes, is going to be Q dot minus W dot is equal to basically, right, the energy, the stored energy, the total energy after dot minus the total energy before dot, right? This is for a steady flow process. I'm signifying that this is a steady flow process because just last time for topic 5, you guys have dealt with steady flow devices. And you will use this more in the context of steady flow. Right? And so now, ang gagawin natin is that we will rethink. Right? We will rethink the, excuse me. We will rethink the processes that we have seen earlier in terms of this, in terms of this equation, right? More specifically, let's say for process 1 to 2, because what we're doing in the first law is we're talking about a particular process and we're getting more details from this process. For process 1 to 2, look, right? We can say that the Q minus W from process 1 to 2 is going to just be the energy at state 2 minus the energy at state 1, aka the change in total energy between state 2 and state 1. We can say this again for process 2 to 3, right? Your Q minus W for process 2 to 3 is going to be E3 minus E2, basically the total amount of energy at state 3 minus the total amount of energy at state 2. And again, we can say this again for states 3 and 1, for process 3 to 1. And what do you guys see will happen? Actually, I think there's a short spoiler in here. But why am I displaying them in such a way? Right? Do you guys see something that we can do about all of these 3 equations? Right? If you guys are seeing this properly now, hopefully, you're able to detect, wait a second, look at that right-hand side. Right? I'll give you guys a hint, right? It has to do with the right-hand side. Look at the right-hand side. Why is that so important? Because now, look, right? This has its negative here. This has its negative here. And this has its negative here. Why is that so important? Because look at what happens next. If we then add everything, we will see that these guys will just cancel. This will all be 0. And more specifically, if you guys see this on the left side, nothing is going to get canceled, right? All that's going to happen is that they're going to add up. And more specifically, something like this. All of the W's in here are negative. And as a result, all of the W's in here, once you add them up, are still going to be negative. If you then put them all into the right side, what will happen is that you will have Q plus Q plus Q, right? From processes 1 to 2, 2 to 3, and 3 to 1 will be equal to the works, right? The sum of the works from process 1 to 2, 2 to 3, and 3 to 1. And basically, we will have another manifestation for the first law in terms of cycles. What we have here is basically the contour integral for your Q is equal to the contour integral for your W. In other words, in simpler terms, right? If you sum up all of the heats, you will get a value that is equal to the sum of all works. So heat net is equal to work net. That's it, right? We said earlier, that your Q1 to 2, right, plus your Q2 to 3, plus your Q3 to 1, oops, sorry, 3 to 1 minus your work 1 to 2, minus your work 2 to 3, minus your work 3 to 1 is equal to 0. If you then put all of these guys into the other side, what you will see is that, well, you just add up all of the heats, and it seems that they are equal to all of the works, which is this thing, right? When you're talking about the first law for cycles, you should think that the total amount of heat that you add or subtract will be the total amount of heat or of work that you get or give, right? That is the first law for cycles. Basically, anything that comes in should come out, right? Anything that comes in should come out. That's it. That's the first law for cycles. Okay, let me see how long I have yapped. We're now at 20 minutes, right? Now, back to this graphical viewpoint, we just said earlier that in a PV diagram, we will have the total net work, right? For the cycle 1, 2, 3, right? We will have in this what do you call this? In this diagram, right? The area that these guys enclose is going to be work net. And so let's try to draw this from another perspective. Let's try to draw it from a TS diagram. And hopefully you guys are ano tayo ito? You guys remember why these two are important as well, right? This is because, right? If you guys remember, right, your work is equal to just your P times V. More specifically, if you want to say your work, that's going to be P times dV. On the other hand, hopefully things are making sense, right? You're getting parallels from each other, right? Your Q is equal to T times S. Or more specifically, your delta Q is your TdS. And well, this looks like an S. And there you go. Right? And basically, you can map out, if you know the pressure and volume at state 1, you can know kung ano yung temperature and entropy nila. Right? Because it only takes two, right? It only takes two, what do you call that again? It only takes two properties for you to completely define a function. Let me continue that thought. Okay, I will now continue the thought, right? Where was I? Right? Once you understand or once you define two independent thermodynamic properties, you know everything else. So if you know the pressure and volume, you should be able to know everything else, including the temperature and the entropy. So if you know state 1 in the PV diagram, you should also be able to graph it in the TS diagram. Right? It just so happens that it feels like parang same lang sila. Is that right? No, actually, they changed. They changed, right? But their position is still relatively the same, I guess, right? So for state 1 to 2, right? If you want to describe process 1 to 2, it's no longer going to be the same curve. I cannot guarantee that, right? It'll just be something else. I don't know how that will manifest in here, but there you go, right? And then you can also try to graph your state 3. I should have put these elsewhere. Parang mas maganda if I show you guys that the PV and the TS diagrams are not going to be the same. But there you go. That is my that is my drawing, right? And for you to go from state 2 to state 3, you also need process 2 to 3, which I really don't know what the is going to be, what the shape is going to be. And from 3 to 1, I also don't know, right? But suffice to say, if you know states 1, 2, and 3, if you know processes 1 to 2 to 3, 3 to 1, if you know the cycle of the PV diagram, it should be no big deal for you to be able to turn it into a TS diagram with enough help, of course, with enough help. And basically, why am I doing this? Because if you guys notice again, right? What is this shape going to be? What is the area of this shape going to be? Well, this is going to be the heat from 1 to 2. What is this shape going to be? This is going to be the heat from 2 to 3. And what is this shape, this negative shape going to be? This is going to be the heat from 3 to 1. And basically, once you put them all together just like you did earlier, right? Just like you did earlier, what you will see is that this is now the net heat. This is now the net heat, right? And as a result, these two, right? So long as you have done everything correctly, these two should have the same area, okay? These two should have the same area. That basically wraps it up for the first law for cycles, right? And basically our definition for cycles. I will now teach you guys, or rather, I will now divulge the two different types of cycles, of thermodynamic cycles for our day-to-day use, and they are power and reversed cycles, right? But how do you classify them? Well, there are lots of ways you can classify power and reversed cycles, but most importantly, I feel like they are classified based on their purpose, aka why did you build this cycle, right? What do you want to get out of this thing? And there are two possible answers to that, which are answered by power cycles and reversed cycles. Okay, let's begin with power cycles, of course, right? These are cycles where heat is added to the cycle. That's why they are called heat engines, right? Power cycles are cycles where heat is added to the cycle or the system so that work, aka electricity, can be generated. What do I mean by this, right? How you add heat and then you get work? It kind of makes sense, right? As in, like, for example, in a steam engine, literally those old things, right? In the trains where you will see these very young boys, like shoveling coal into the front of the train, is that what they're doing is trying to add heat to the engine via the coal that is being burned so that the train can continue to move, right? In this case, you can use the first law for cycles to determine that, okay, if I add heat to the system, what will happen is that I gain work, right? If your net heat is bigger than zero, aka if it's positive, what's going to happen is that, well, you get positive work as well. And what does that mean? That means that, well, you are going to get that work. Okay? Just please remember that this is a net value we're talking about, huh? Right? It does not mean that if you add 100 worth of heat, you will get 100 worth of work. Right? This is a net value. We're not talking about a gross value here. Right? We are talking once all of the taxes, quote unquote, once all of the thermodynamic taxes have been applied, that is the net value that you are going to get. Okay? And just to understand, just so that you guys understand, there are many types of power cycles. Just off the top of my head, there are 10 that I'm supposed to know as a mechanical engineering graduate and I guess like a registered professional, I guess. Right? There are 10 and there are many acronyms that are what do you call this? That are available out there, right? In our review center, they call it the Berks load. So I will write it down now. DBERCSLOAD, the Berks load, right? But I've taken the liberty of trying out a different kind of mnemonic. Kasi ang dami, there's so many mnemonics like I can name. I was making some while you guys are finishing your quiz 2, I think. Basta, ano yun, I came up with many uh, acronyms. Like, for example, I don't know. Like, I came up with bold scared. Pero sabi ko, it's not very appropriate to do this right now. And there is a distinction pa between these these acronyms. So I'd like to introduce you to the acronym I will use. Let's say your friend who's a bit weird recommends you songs or movies or paintings or whatever, or things to try. Those are some oddball recs. Please note there's only one L, right? Para hindi kayo malito, oddball recs, right? And so the thing about this is that oddball recs also correspond to how heat is added, right? What do I mean? We will have, for the oddball, we will have the auto, diesel, and dual cycles, right? And for the BAL, we will have the Brayton, Atkinson, and then Lenoir cycles. It must be noted that for the people who like cars, right, you guys will notice three or two that you might know, the auto cycle and the diesel cycle. These guys on the left-hand side are what we call internal combustion engines, right? Internal combustion, aka what happens is that you burn something inside of the gas, right? Inside the system that you're trying to work on, right? So for auto and for diesel, right, which corresponds to gasoline and diesel engines, most specifically, or sorry, respectively, what happens is that, well, you either have a mixture of air and fuel inside of the combustion chamber in the pistons of your car or your vehicle or whatever, or air is compressed and then it's injected with fuel and then bang, 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 blah, blah, blah. You get energy, you get work so that your car goes vroom, vroom. Very, very technical for like a professor, right? And if you're wondering about the and if you're wondering about the codes, if you want to call them codes, right? If you're wondering about the codes on the sides of the cycles, well, just remember the two I will tell you to remember later, right? And now for the Rex naman, we have the Rankine, Ericsson, Carnot, and Stirling cycles, right? These are now based on based on patterns. These are now external, right? External combustion engines. What this means is that basically the hot part comes outside of, kaya nga external, right? It comes outside of the actual working fluid, aka you're not trying to heat up the fluid by combusting it, right? What you're trying to do is that you're trying to heat it up, right? You're trying to add heat to the cycle by, I don't know, like putting it in contact with something that is hot, right? Like, for example, you boil water in a boiler. It's not like you're trying to combust the water, it's just that you're trying to heat it up with something else outside of the cycle, which is the, I don't know, the air that is surrounding the boiler that it makes it really hot, and then there you go, right? That makes your power plants go boom boom. There you go, your power plants, right? And for these, I will just have you memorize Rankine and Carnot for now, right? That'll be the things we are using here. So for Rankine is SPSP, and then for Carnot is STST. So hopefully you guys already have an idea of what's going to happen here, okay? And so now we will have an example, which is the Rankine cycle. So hopefully you guys remember the code, right? And a Rankine cycle basically is a power cycle using the vaporization properties of steam to convert heat into work. This is one of the more unique cycles because it takes into account, or rather its working fluid is steam, right? Or water, sabihin na natin water. And it is composed of these four processes. We have process 1 to 2, an isentropic expansion at the turbine. From process 2 to 3, isobaric heat rejection at the condenser. Process 3 to 4 is an isentropic compression at the pump. And process 4 to 1 is an isobaric heat addition at the boiler. Okay. That was a lot of information. Okay. And the thing about this is that, well, you're going to have a hard time, really have a hard time, understanding the Rankine cycle unless, I believe, it's my belief, unless you memorize the code. If you guys remember, for the Rankine cycle, the code is SPSP. What does that mean? SPSP. Isentropic, same S. Isobaric, same P. Isentropic, same S. Isobaric, same P. That is how you're supposed to, I suppose, memorize the Rankine cycle, right? It's best memorized through these codes. That is at least my belief, right? And of course, you're going to have to memorize as well. In a Rankine cycle, the infrastructure remains the same. It's always turbine, condenser, pump, boiler, right? Okay. So in this case, a turbine, right, expands the fluid, right? Expands some really, really hot steam, right? And then a condenser, well, you know what? Ikwento ko na lang on this next slide. This is the schematic diagram of a Rankine cycle. There you go. Boiler, a turbine, a condenser, and a pump. Right? If you guys remember this trapezoid shaped thing, right? That is for the turbine. And this thing for the pump. Okay? Now, let's start off understanding where the states are in here. And this is one of the more rookie mistakes, right? Please understand that your steady flow devices are the processes. Okay? Just because you see an arrow does not mean it is a process. In fact, state 1 is this thing, is this line right here. This is your state 1. Okay? What happens is that this state 1, we usually call state 1 the hottest or the highest pressure fluid, or rather highest pressure, highest temperature of the state of the fluid, right, in the cycle. And what basically happens is that if I'm saying that this is a very hot, very energetic, very high temperature, high pressure kind of steam, that is perfect conditions for a turbine to understand, to develop electricity, right? What happens is that it will take, right, the turbine will take some amount of energy from the very energetic state 1 and then turn it into work, turbine work. As a result, what you guys feel would happen, right? As a result, sabi natin there's lots of energy here in state 1, but then some of it gets stolen, quote unquote stolen by the turbine so that we can get the work, right? That is what a turbine is for. As a result, state 2 is now no longer very, very energetic. But I will tell you right now, it's still steam. And the thing about a turbine is that by its mechanics, this is a high pressure, right? This is a high pressure state at state 1, and correspondingly, once it expands, right? Once it expands this fluid, it will now be at a lower pressure, right? I will tell you right now that state 2 is still quite hot. However, it's in a low enough pressure that if you do this, it will not work. Even though it is still quite energetic, it will not work because it is now at a lower pressure. So our goal for the rest of this cycle is to bring back this state into high pressure. And how will we do that? Right? We know that this doesn't have as much energy as it has. And the thing about this is that we can use a compressor, right? A compressor, what it does is that it compresses the thing so that it becomes higher pressure. But the thing about that is that it's going to take a lot to compress a gas, much less a really hot gas. It will ruin your equipment if you try to compress a really hot gas. So a better, safer option would be a pump that works with liquid water. And so what do you need to do to turn this steam into liquid water? Well, you condense it via a condenser. What will happen is that this steam, right, this steam, which is still quite hot, but is no longer at the correct pressure, is going to condense, aka at the last point, or rather, paglabas sa condenser, your fluid, state 3, is supposed to be saturated. AKA, it's just gonna be a liquid talaga. And moreover, what does a condenser do? Well, it removes some of the heat from state 2 and puts it out into the atmosphere or to wherever, actually, right? What a condenser does is that basically it throws away the heat from the steam so that in state 3, right, ang lalabas dito will be a saturated liquid. Always, ha, guys, always. Saturated liquid always for state 3. Why do we need it to be saturated liquid? Because a pump, more specifically a pump, not just a compressor, but a pump, right? A specific type of compressor only deals with liquid, right? You cannot have any bit of steam in there unless you want to wreck the pump. I mean, if you want to do that, go ahead, right? And the pump now gives it energy, right? The pump now supplies energy to the saturated liquid, not so that it can turn into steam again, diba? If you add more energy to the saturated liquid, it will turn into steam, right? It's not going to do that. What it's going to do is that it's now going to take it up to a higher pressure at state 4 so that the process can repeat, right? Once you add more heat into this boiler, right, you will be able to successfully boil this state 4 into a high pressure, very energetic, very high temperature, high pressure kind of sample, and babalik tayong state 1. Okay? I'm at 40 minutes. Oh my gosh. Okay? And so that is how the Rankine cycle works. If you guys need another kind of round of explanation, don't worry. Just like rewind. Okay? And if you want even more, here you go. Here we will have the TS diagram of the Rankine cycle. I've put a small version of it on the left. And now we will have a gigantic TS diagram for here, right? And because we are working with water, there will be a saturation curve. Why is this blue? Oh, I didn't know this was blue. Okay, but okay. I think I set this to black. Anyway, you know what? That is the saturation curve, hopefully, right? For those people who are still stuck in topic 2, matandaan natin, right? This is the saturation curve. The region to the left is, right? I'll give you guys some time, like pause and think about it, or AKA like look at it from your topic 2 again. The region on the left, this thing, is the compressed liquid region. Okay, right? For the people who are like, ah, man, right? Hopefully now you can see that the region on the right will be the superheated vapor region, right? And then for the last one here in the middle, we will have the saturation region. And now for the, what do you call this? For the next 2, right? For the next 2, we will have what we call these things. Do you guys remember these things? Hopefully, if not, then that's fine, right? This is what we call an isobar. An isobar, another term for that thing is a constant pressure line. Kaya isobar, right? Iso, same, bar, pressure. Same pressure. Constant pressure line, basically. Right? And you might be wondering to yourself, like, why is it this weird thing? Right? Why is it increasing and then suddenly, whoop, it remains constant inside the saturation region and then it continues to increase again, right? The answer to that is that if you guys remember, in the saturation region, once any fluid enters the saturation region, their temperature and pressure will become locked, right? As a result, if you're trying to say, okay, constant pressure ako dito, once you enter the saturation region, your pressure and temperature become locked at the, this is not pressure. This is supposed to be temperature, yan, Tsat, right? It will become locked with the saturation temperature of the fluid, right? And this will be our high pressure line. Okay, this will be our high pressure line. And that means that another lower one, will be the low pressure line. So why am I drawing this? Because now you guys need more context as to what is going to happen next, right? What's going to happen next is that we will now graph in a TS diagram this, right, the Rankine cycle. Let's first start off with state 1, right? State 1, I said, was very energetic, very high pressure, right? I keep repeating that thing, high pressure. That means that it should exist somewhere in the high pressure line. And moreover, sabi natin, kakagaling lang niya, it's just finished boiling from the boiler. So we'd expect it to be somewhere along this region. Why? Right? Because it just finished boiling. Therefore, at the end, you should expect it at the very least to be a saturated vapor, right? It just finished boiling, right? And the thing pa is that it can go even further than boiling, aka superheating. It can now turn into a superheated vapor, and we will find our state 1 here, right? Our state 1 is there, and what will happen is that the turbine will now expand. The turbine will now expand, but the thing here is that we have to remember as well, right, where state 2 will be. I know that because it's expanded, it will now lie somewhere in the low pressure line. Pero, we have to understand again, what is the process between state 1 and 2? The process between state 1 and 2 is, from the Rankine cycle, we said that this is SP. Right? So for the Rankine cycle, from 1 to 2, this will be constant entropy, S. And as a result, okay, how do you draw a constant entropy process in here? Well, this is the entropy at state 1. This is the entropy at state 1. We just said that it's isentropic, so this should also be the entropy of state 2, which means, I see, right? That means that an isentropic line, or rather, an isentropic process can be drawn as just a straight line up or down. In this case, down, because you are expanding. Boom. Right? This is now your state 2. And what connects them is this straight line right here. And mind you, yun nga, because this is a turbine we're talking about, you will see in here that there will be work that is extracted. Right? There will be work that is extracted, that is WT, aka the work of the turbine. And now we go from 2 to 3, right? Which is the condenser. And again, for the condenser, what it's doing is that it's rejecting heat. It's rejecting heat how? Up to how far? Well, wala namang magiging change in pressure. If you guys remember, from 2 to 3, it is isobaric. So it will remain in the low pressure line. And sabi natin, always in state 3, this will always be a saturated liquid. Unless I say so, it's always going to be a saturated liquid. And so, well, how are you going to connect these two things isobarically? Well, they're already in the same pressure line, and you just connect them like this. And as a result, what will happen is that you will release heat, right? You will release heat. You will reject heat. Okay? That is now heat rejected, QR, right? And from state 3 to state 4 again, right? SP. So again, we are going to go through another constant entropy, right? Constant entropy process. State 3 is going to be equal to state 4. So we probably know where state 4 is. It's going to be there, right? At the high pressure line, because, well, what a pump does is that it pumps water up to a higher either elevation or a higher velocity or a higher pressure, right? That is now your process 3 to 4. And what you notice, the pump work is very small. And this is also another This is also another advantage. Yes, I would call it an advantage. This is another advantage of trying pumps instead of compressors. Because, well, look at that. The work is so small compared to the work of the turbine. And now, how do you get from 4 to 1? Again, 4 to 1 is an isobaric process. So you literally just connect the lines together. Not like this, huh? Not like this. But you follow the high pressure line. Right? You follow the high pressure line. Right? And that is how you add heat. Kumbaga, you're going to now trace, right? Oh, I'm still compressed liquid. Oh, I'm now saturated, and then I will slowly turn into steam. I'm now full of steam, and now I become superheated. And this is the Rankine cycle's TS diagram. Okay, so now the Rankine cycle's TS diagram. Okay, this is it in all its glory, right? You will have turbine work going out. You will have heat rejected going out. You will have pump work going in. And then you will add even more heat. Okay? And now, if we put this all together, right, this thing, right, this thing, what is this thing, right? This is going to be the heat added, right? If you guys remember, there's a massive arrow in here that says Q added. What does that actually mean? That actually means the area of this thing. If you remember, we are in a TS diagram. That means that any area in this case will now be attributed as heat. E ngayon, magtataka kayo, what about states, processes 1 to 2 and 3 to 4? The thing about them is that, well, they are isentropic, aka they are adiabatic. So now I will ask you, in processes 1 to 2 and 3 to 4, do you see any heat being transferred? The answer ideally would be no, because nga, under an adiabatic process, it happens so quickly that the heat has quote unquote no time to go out or go into the fluid. So as a result, we only have two types of heat in here: the heat added from state 4 to state 1 and the heat rejected. How do I know it's heat rejected? Because, well, it's right to left. At states 2 to 3, so be negative. And again, also, right, it's heat rejected. Right? So heat going out of the system is going to be negative, of course. Right? Okay. Now, I think that is it. And once you combine these two, aka, diba? The big area, oops, sorry. The big area, and here is this weird, I don't know how to describe this thing. Before, when I was studying thermodynamics, I always thought of this as a horn. So I was thinking this is like a rhinoceros, something like that. Sadly, you guys won't. I don't know if it's sad, but for you guys, it will not go as far as ways to improve the Rankine cycle. But for the mech-engs, for the mechanical engineers out there, they will have even more horns. Just remember that in the future, right? If we combine these two areas, this positive one and this negative one, aka we cancel out this negative region below, we will get this shape, right? Sorry, let me see that again. Oh yeah. All right, we will get this aggregate shape, which is going to be the heat net, right? This is going to be QA plus QR, but QR is negative, so it's actually going to be like QA minus the value of the QR that you got earlier, right? And because of the first law of thermodynamics for cycles, we now know that this heat net is also going to be work net. Okay? And now, why is this important? Because we will end on this topic. We will end on performance, right? Performance of power cycles. The thing about this is that how will you know now if this cycle is any good, right? How will you know if this cycle is any good? Well, that is where the final frontier of engineering is, right? We will, ano tayo to, before, well, back then, right, engineers were making things. And I feel like a lot of people who are in engineering become very insecure, right? Become very insecure because I have been. Sorry, let me see. Okay, 53 minutes, just a few minutes more. I have been insecure because compared to the people who get into news, who get into the news, like for example, oh, this guy just invented this thing, or this person just found a way to blah 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 blah, right? And I don't know, but like that sometimes gets to me, and like, wait a second, I'm supposed to be an engineer. I'm supposed to make things, but I don't. I just study these things, and now this is where we get to shine, I suppose, right? The final frontier of engineering, if you do not make something new, that's completely fine. Engineering also has to do with improving the performance of something, right? If you can somehow manage to, I don't know, create even more, get even more from a particular object, product, or something, right? If you increase, basically, if you increase the efficiency of something, that is amazing, right? Not only are you working with something that is already been made, it's basically constrained, you are trying to, and you are effectively creating ways to improve the performance of that thing, which is great, right? Better for everyone, right? But sorry, aside finished, efficiency is the measure of how well a machine operates, right? How do you compare efficiencies? How do you even compute efficiencies? Well, you just compare its output by the input that you've given it, right? It's efficient if, for example, you give 100 of something to a machine, right? You expect it to give you 100 back, right? But if it only returns 50, right? If it only returns 50, well, you can say it's 50 over 100 or it's 50% efficient. That is how we will define efficiency for now, right? This is the Greek letter eta, right? Eta, E-T-A, right? This is their letter E ata. Pero I don't know why. Why not use epsilon or something? But there. And how you draw this is basically you draw the letter N, but you elongate one stalk. There, right? And some people draw it like this. I draw it like this stylistically. Like for example, you're a bit drunk. You draw the letter N, right? So that is our efficiency. But you can also go with letter E, right? Or even EFF will work. I'm not very particular about this. Basta it's going to be output over input. Why is this important? Because we have to reconcile the, what do you call this? The concept of efficiency in power cycles, right? What do we do in a power cycle? Basically, you add heat so that you can generate work or generate electricity. So this clarifies things, right? Our input is the heat that you add, and your output is the work that you generate, right? Very easily. And as a result, we can now say, wait a second, now I can recontextualize efficiency as thermal efficiency. Why thermal? Because you are adding heat. You're expecting work. Therefore, thermal efficiency is defined as the work you generate minus tuloy, all over divided by the heat you add. Right? NTH. Right? Eta TH pala rather, sorry. TH for thermal. Right? Some people do it ETH. That's fine. Some people do it ET, which is also good. Okay? That is how we measure the performance of these power cycles. And now we bring back this thing, right? What is this region we are talking about? This is the region where we added heat. And basically in the end, this region right here, which is shaded, is going to be the net heat. Or based on the first law, right, for cycles, this is also the net work. And so if you guys manage to find the areas of these two shapes and you divide, what you will get is your thermal efficiency, right? Basically, that is what happens. Okay? So hopefully that is clear because I think I will end there. Yeah, sakto. Right? This is 1 hour of our what do you call this? Of our lesson. But actually, yeah, nga pala, meron pa palang, never mind. There's a few more minutes here, right? And the thing about this is that for us to make sense of this just a little bit more clearly, right, I will bring back the original Rankine cycle diagram with all of the heats and all of the works that you see. For process 1 to 2, you get turbine work. Process 2 to 3, you get heat rejected from the condenser. From process 3 to 4, you get the pump work by the pump, right? And from 4 to 1, of course, you add even more heat. Okay? And as a result, what we can do is, wait a second. Didn't we just have, I don't know, like in steady flow cycles, didn't we do something like this? Like, isn't this thing one system already, right? From a turbine, this is one system, right? This is, ano nga ba ito? This is states 1 to 2, right? From states 2 to 3, right? We have a condenser here. Isn't this also, right? Isn't this also one more state, one more system? Isn't this also one more system from state 3 to state 4, right? And isn't the boiler, right? Isn't the boiler also another system? The thing about this is that yes, all of these guys are systems, right? You can apply the first law of thermodynamics to each and every single, right, each and every like system in here. So you will have four systems. But the thing is, as we've learned in topic one, in the very, very beginning, is that you decide what the system is, right? You decide. You ultimately, we are the ones responsible for naming what the system entails. And in this case, you can choose not to cut it like this. You can choose not to cut it like this. You can choose not to cut it like this. You can choose not to cut it like this. Instead, what you can do is include everything. You can choose to include everything. This is my system now. And if that is my system now, do you guys see it can be simplified to just the cycle itself? And notice now, in all of these systems right here, they are steady flow devices. In a sense, they are all open systems. In here, do you guys see a particular region where mass goes in or mass flows out? Because to me, I don't see anything, right? A Rankine cycle in this case is now an example of a closed system. Very interestingly, right? No mass goes in, no mass goes out. It's literally water or steam just flows in and out and in and out and over again. And what happens is that only energy is transferred, right? This will be another way for us to see that, look, whatever goes in QA plus the pump work should be equal to whatever comes out, the turbine work plus the heat rejected. In this case, what you can actually do is repurpose, right? Put the R on this side, put the WP on this side, and you will get, right? And you will get QA, heat added minus heat rejected, is equal to work of turbine minus work of pump. Basically, this is the heat you add, this is the tax, quote unquote, right? This is your heat net. And then this is now also your work net, right? This is the energy generate, this is the tax, right? That you have to give for it to be able to close the loop. And again, based on the first law for cycles, these two have to be the same, right? And there you go, right? We can simplify any cycle, any power cycle, sorry, in this regard, through this drawing, right? We have what we call here heat sources and heat sinks. Basically, what is the heat source of a power cycle, or more basically a Rankine cycle? Well, the heat source is where you get the heat. Where do we get the heat? We get the heat from the boiler, right? This is now the boiler. And the heat sink in this case is basically, well, where you're going to dump the heat, right? Where is this thing? This is the surrounding air. This is basically everything else, right? And these guys, these boxes in here, the top box and the bottom box, the heat source and the heat sink, are what we call thermal reservoirs. By reservoir, they mean they store large amounts of heat. In this case, the heat source stores a lot of energy, or stores a lot of heat that is from a high temperature source. The heat sink has a lot of heat at a low temperature source. So what happens is that naturally, well, we'll find that out, right? Heat should flow from hotter to colder, right? Heat should flow from hotter to colder. And that goes into the power cycle. Some of the high temperature heat goes into the cycle, which is the thing that you're supposed to add so that you generate the work, right? The work is here. And then it just so happens that waste heat in the form of the heat rejection exists, right? And basically, this is how we're supposed to think about any power cycle out there. What happens is that for any power cycle, again, you add some heat from a hot thing, from a hot source, right? A boiler or something, you generate heat from it. Sorry, you generate work from it. And then it just so happens that a byproduct is going to be the heat that you reject, right? In this case, right? In the Rankine cycle, what happened was that the Rankine cycle steam at the lower pressure point needed to be elevated again. So, well, you have to turn it to water. That is the consequence, right? And so, well, that is the end talaga. That is the legit end this time around. Okay, right? Yes, because for Thursday, I will be discussing reversed cycles this time around, right? So if you guys have any questions, please do not hesitate, right? Please do not hesitate to ask me. Either, I mean, like I'm gonna upload this on YouTube. This will become public, so I don't know, just like comment in there or something, or just send me a message on Canvas, or just reach out to me so that I can address your concerns, right? Thank you guys. I hope you do get through the whole length of this thing. And as part of your attendance, right? As part of your attendance, I will be posting an announcement. And in that announcement, I will be taking your attendance, aka I will be looking at whoever has watched this video. Please reply. I don't know. You know what? Reply something that you are currently seeing in the room that is orange. I don't know how this is going to work, but yun nga. Please reply something you see in the room that is orange. Not my room, but like your room as you're watching this right now. Reply. Okay? So that I know when you watch this thing, right? So that I know when you watch this thing, because if you do reply, I will give you, you know what? Let's incentivize this, right? I will give you a plus, I don't know, +2, +2 in your final examination. Yun na lang. All right? So I will not be announcing this in the announcements at all. Just reply an orange thing in the announcement, right? Okay. Thank you guys very much. I will see you on Thursday.